Hello. Okay, so this is me back on our series of videos here about Intro to Integrals, and I'm going to do now. Previously, we kind of worked through the kind of a little bit of the theory about it, and specifically some examples about how we would calculate or estimate the total distance traveled by a car. If it was going at constant speed, if it was going faster, or if it was increasing in speed, or if it's decreasing in speed over time. We saw with the decreasing and increasing ones, where the speed wasn't constant, we had to use this left-hand or right-hand rectangle sum method to get an estimate of the distance traveled, since we didn't know how to calculate the exact area under the curve, although we're headed in that direction. What I'm going to do here is we're going to do some specific examples from the homework so that you can follow these when you're doing your homework, okay? Each of the examples takes a little bit of time to get through. So rather than trying to do one big, long video with all of the examples, what I'm going to do is I'm going to do one example per short video. So this will be example 1, okay? Now, here's the situation. A car comes to a stop 6 seconds after the driver applies the brakes. While the brakes are on, the following velocities are recorded. Now notice in this one, they don't give you a graph. They just give you data. So at 0 seconds, the car was going 100 feet per second. After 2, it was going 80. After 4 seconds, it was going 30. And after 6 seconds, the speed was 0, meaning it had come to a complete stop. Okay? Now here's what we're supposed to do. We're supposed to give the upper and lower estimates for the distance that the truck traveled after the brakes were applied. Okay? And then we're going to sketch a graph of the velocity against time and show the upper and lower estimates, meaning that we're going to graph this data, and then we're going to sketch out the rectangles, the left hand and the right hand sum rectangles, so it'll give us an upper and lower estimate of the distance traveled. So anyway, so actually we're probably going to do B. We're going to go ahead and do B first, and that'll give us the answer to A. Although in the end, you may look to see that, once you get the scheme on these table problems, you don't necessarily need the rectangle graphs. Although in the beginning, I'm going to need you to draw these out fair and square. Okay? So let's see here. Okay, so first off, let's plot the data. After 0 seconds, at time 0, it was going 100. I'm going to plot that here. And I've got two different graphs. So this is going to be the upper estimate, and this is going to be the lower estimate graph. Okay? So here, this is speed. This is time. So I plotted at time equals 0, a speed of 100. After 2 seconds, it was 80. That's about there. After 4 seconds, it was 30. This is 50, then 30 is down here, right? And after 6 seconds, it's 0, meaning that it stopped. Now you can see that if I just kind of draw a smooth curve through it, that kind of would give us, an idea of what our stopping speed function would look like, y equals v of t. So what we really want in order to calculate the distance that the car traveled from 0 to 6 seconds while it was stopping, we'd need to find the area under this curve. Well, we don't know how to do that yet, so we're going to estimate that using rectangles, right? Now we want the lower and the upper. So this one will be, what did I say? This one will be the lower estimate here, right? And so that means we need to designate intervals for our rectangles to be in. Well, notice here that our time intervals, our time measurements, are conveniently split into 3 2-second intervals. So this will be the first interval. This will be the second. That'll be the third. So we're going to have n equals to 3 sub-intervals, right? Right there. N equals to 3 sub-intervals, right? And so we're going to, each one with an elapsed time of 2 seconds, 0 to 2, 2 to 4, and 4 to 6. So on here, I'll mark those on the graph. Here's the 0 to 2 second one. Here's the right side boundary of the 2 to 4. Here's the right side boundary of 4 to 6. Now, if we want to give the lower estimate, that means that we want to have our rectangles. Those are the rectangles that are inside, that are underneath the curve. So that means for this decreasing function, I'm going to get the height of the rectangle on the right side boundary here at 2 seconds. Just like that. Right? I'm going to draw the top of the rectangle over, just like we did in the other examples. So from the right side boundary over to the left side boundary for that interval, and that's the rectangle there, right? Now for here, to get the rectangle underneath, again, I'm going to start at the right side boundary and go to the left side boundary, right? And then over here, so this one, so we want the area of that rectangle. So this one, they each have a delta t of 2, right? This one's got a delta t of 2 when we get to it. The area of this one is 2 times 80. And we don't really need to use that. We don't really need to read that off the graph. We're just going to use the 2-second time measurement here. 2 times 80. And then at 4, the right side boundary, we're going to use the 4-second boundary, or the 4-second measurement, which is 30. Now how about this third rectangle here? The right side boundary is 0. So that means, and I'm just going to indicate it here, in effect, we've just got a rectangle but of 0 height. Okay, it's very important when we're using the right hand or the left hand sum that we don't mix and match. They're always either all left side boundaries or right side rectangles. We don't have some of each and some of the other. So these are only going to be right side ones, which forces us to have over here, as you can see, a height of 0. Right? So this is 2 times 0, and that's 160, that's 60, oh look, that's 220. You know, and then this is, we're traveling in feet per second, so this is feet, right? And so 220 feet is our lower estimate, and I'll write that up there for the distance traveled. Now to get the upper estimate, we graph the data again. 100 for 0, 80 for 2, 30 for 4, 0 for 6. So we've got that same curve that we want to get the area under, but now we want the rectangles that are above it, the upper estimate. That means we're going to use, as you're going to see in a minute here, the left side boundaries. I marked the same intervals off, 0 to 2, 2 to 4, 4 to 6, right? And the delta here, the delta t is still 2, right? But you see here now the upper bound, to get the upper estimate, I'm going to connect on each of their left side boundaries, like this. Right? And I get the area under those rectangles. Well, that's going to be 100 is the height there, because we're using the left side boundary, 80, and then 30. So you notice we're still using these measurements up here, but now since we're using the left-hand boundaries, we're using 100, 80, and 30 for the heights of the rectangles. So 2 times 100, 2 times 80, 2 times 30, and that's 200, that's 160, that's 60, that adds up to 420 feet. 420 feet. So 420 is the upper estimate. And you can see here, there's quite a gap between those two. We know that it can't be as low as 220 because there's a lot of leftover area that wasn't accounted for, and it can't be as high as 420 because there's a lot of area included in rectangles on the upper ones that aren't really under the curve. But we do know that it has to be somewhere in between. Okay? All right, so that'll be example number 1, and I'm going to do example number 2 next.